All right, we are looking at section 8.5 and 8.6, where we are going to write and graph exponential growth and exponential decay functions. So if you look here on the screen right here, exponential functions are written in any form of y equals a times it by b raised to the x power. Okay, so the first thing that we got to do is we have to be able to write a rule for the exponential functions. And here is how we do it. So first step is we must be able to find a in the function. To find a in the function, it comes from the value we get for y when x is 0. So if we look at the chart here, x is 0 right here. We look at what y is 2. So that means in this particular chart, a is going to equal 2. The next thing is we have to find the value for b. Once we find b, or once we find a, we can look for b by taking the product of y as x increases by 1 unit. So if you look here from 0 to 1, this is 1 unit. And so between 1 unit, you just multiply 2 times it by 3, which gets us 6. Same thing goes here, 6 times by 3, that gives us 18. So the product of what it was each time was 3. So that means that b is 3. And we can say that the rule will be y equals a, which is 2, times it by 3 raised to the x power. Okay? So to write the rules for any one of these examples, I have a chart with some data on it, x and y values. So the first thing you got to do is you got to find out what a is. All right, easily you just look for where x is 0. X is 0, y is 27. That means that a is 27. And then we take the product as it increases by 1. You multiply 27 by 3, that gets us 81. Same thing goes here. You multiply it by 3, you would also get 243. So that means that b is 3. So that means that my rule will be y equals 27 times it by 3 raised to the x power. Next example, b, same thing. I look at where x is 0, y is 1, so that means a is 1. And then I have to multiply 1 times 2 to get 2, multiply 2 times 2 to get 4. So it's consistent. That means b is 2. So my rule will be y equals 1 times it by 2 raised to the x power. Or you can leave it as y equals 2 raised to the x power. So if you don't see any value that's being multiplied by raised to the x power, you make the assumption that a will be 1. Final example here, I look at where x is 0, y is negative 3, so a will be negative 3. To find b, I multiply, looks like this by 2, multiply this by 2. It's consistent, so that means b is 2, so my rule will be y equals negative 3 times it by 2 raised to the x power. The next thing we got to do here is graph exponential functions. So there's 3 things we got to do. The first thing we got to do is figure out what a and b are in the general formula. The general formula again was y equals a times it by b raised to the x power. Once we find a and b, we plot 0 comma a, and then we finish making the table. So in this particular example, we got y equals 2 raised to the x power. Since there's no product there, we remember we make the assumption that a is 1, and that means that b, which is raised to the x power, that's going to be 2. All right, and so now we plot the point 0 comma a. Well, a is 1, so I write in 0 comma 1. I can plot the point, which is right there. From here, we know that b is 2, so that means we just simply multiply it by 2 to get this value. 1 times 2 is 2. Multiply it by 2 here. 2 times 2 is 4. Okay, now to go backwards as a negative number, instead of multiplying 1 by 2, we are now going to divide 1 by 2 to get the reverse. So 1 divided by 2 would be 1/2, and 1/2 divided by 2 would be 1/4. So we just fill in the rest of the chart. -2 comma negative or positive 1/4, -1 comma 1/2, 0 comma 1 we already got, 1 comma 2, plot that point, 2 comma 4 is right here, and then our exponential function will look something kind of like this. Okay, and then the final thing that we're going to look at is domain and range. So from past lessons, the domain is considered to be all of the x values of the function, and the range is all of the y values of the function. So looking at the graph is going to help us decide on the domain and range. So the domain, all the x values, what question you have to ask yourself is there any value of x that you could not use on the graph? Looking at all the negative values, looking at all the positive values, and looking at 0. There's not one value, whether it's negative, positive, or 0, that you could not use as an x value on the graph. So now I'm going to say that the domain will be all real numbers. And here's the symbol for all real numbers. Okay. The range is a different story. So now if you look here, try to highlight it as best I can. If you look here, the graph is positioned in the positive area of the y value. Okay, it's all above the x-axis. None of it is below the x-axis. So what that means is y could not be a negative number. So my range in this case is going to be y must be greater than 0. And so here's where people kind of get a misunderstanding and stuff like that. So let's say, usually it's easy to determine whether it's a a positive number. Well, let's just say that x is a really large negative number for this particular equation. Let's say it's at like -50. So if I were to plug this into the y equals 2 raised to the x power, substituting that in, I would say that y would equal 2 to the -50 power. Well, going back to our rules of negative exponents, we can always turn that into a positive exponent by placing it into the denominator. So I can say that this is the same thing as y equals 1 over 2 raised to the positive 50 power. Right? Well, I don't know what positive 50 is. I just know it's a really large number, but it'll be 1 divided by that really large number, and it looks like a really small decimal. Not quite hitting 0, but very, very close. So that's how that graph reflects that almost being at 0. So in this case, domain is all real numbers. The range is y is greater than 0. Okay, you may see a trend with that. So if we look at this example here, we have y equals 4 raised to the x power. We need to figure out what a equals and what b equals. From the general formula, a will be 1 in this case, b will be 4. So making our table, so I make -2, -1, 0, 1, and 2. 0 with x goes with whatever a is, and so that's going to be 1. And then to find out the values that increase, I simply multiply it by what b is, which is 4. So I get 4 here, and I get 16 over here. To find it in reverse, I simply divide 1 by 4. So 1 divided by 4 is 1/4. 1/4 divided by 4 will be 1/16. You have to plot the points. So I got -2 comma 1/16. That's really close to 0, but not quite. -1 comma 1/4 is here. 0, 1 is here. 1 comma 4 is right there. And then 2 comma 16 is well off the graph, so I'll just say it's right over there. And then I make my graph like so. And finally talk about domain and range. The domain in this case again is all real numbers, and my range, if you look, will be y again is greater than 0. Y equals 2 times 5 raised to the x power. In this case, a is 2, b is 5. Make my table. X and y, -2, -1, 0, 1, and 2. 0 gets attached with the y value, whatever a is, so a is 2. This now gets multiplied by 5. 2 times 5 is 10. 10 times 5 is 50. In reverse, 2 divided by 5 is 2/5. And then 2/5 divided by 5 will be 2/25. Graph the points. -2 comma 2/25. Again, really small, really close to 0, but not quite. -1 comma 2/5. Somewhere right about there. 0 comma 2. 1 comma 10. And 2 comma 50 is well off the graph. So as we look here, looks something kind of like so. And again, domain is all real numbers. You can choose any value for x. And the range again is y is greater than 0. Okay. The last one will kind of change it with the range. So if we look here, y is equal to -3 times it by 2 raised to the 2x power. A is -3. B is 2. Make our table. I got -2 comma -1, 0, 1, and 2. 0 will be with y is attached to whatever a is, so that's -3. To find the rest of the numbers, we times it by 2, so that's -6. Times it by 2 is -12. Now we divide it by 2, so this will be -3/2. Divide this by 2, we get -3/4. So plot the points. -2 comma -3/4, about there. -1 comma -3/2 is there. 0 comma -3 is here. 1 comma -6 is here. And then finally 2 comma -12 is about here, a little bit off the graph. And make my exponential function graph. Okay, now here, domain, it's still going to be all real numbers. There's not one answer for x that I couldn't choose. But now the range is going to be now y is less than 0. If you notice that everything is now below the x-axis and there's nothing on the graph that's above the x-axis. So now that's where I change my value for the range. Okay. Last page, we are talking about being able to write, or at least be able to identify, the difference between exponential growth and exponential decay of functions. So if you look at this graph here, this is an example of exponential growth. And this graph here is an example of exponential decay. All right, two common things for both growth and decay. During the general formula here, y equals a times by b raised to the x power. Both growth and decay, a must be greater than 0. So a must be positive. So if they're not positive, it's neither a growth nor is it a decay. What separates them is this. The value for b for growth must be greater than 1. For the value for b in decay must be in between 0 and 1. So like a fraction or some kind of decimal that's in between 0 and 1. So that's something that we can identify. So the last thing that we want to look at is we're given a series of equations, And all I want us to do is be able to identify if this is an exponential growth, exponential decay, or neither. So right off the bat, I want us to determine what values are going to be neither. So all I got to identify is where A is negative. And I see A being negative here, and I see A negative in this example. So these two equations are neither a growth nor are they a decay. So they're neither. All right, so if I look at the rest of the examples, A is positive with 3, 2, 0.5, and 4 respectively. So now we can go about looking if they're growth or decay. So for the first example, y equals 3 times it by 0.75 raised to the x power. 0.75 falls in between 0 and 1, so this is a decay. The next, y equals 2 times it by 1/8 raised to the x power. 1/8 falls in between 0 and 1. That is also a decay. All right, the next one is right below it. Y equals 0.5 times it by 2.8 raised to the x power. 2.8 is greater than 1, so that's a growth. And the last example is y equals 4 times it by 1.5 raised to the x power. 1.5 is greater than 1. This is also exponential growth. All right, and that is being able to write rules for exponential functions and determining if they are decay and growth. Hope this helps. Until next time.